Good evening, everyone. So today we start a very important topic, that is Ampere circuital law. So what happened in Ampere circuital law? Line integration of magnetic field, that is B dot dl, that is equals to mu naught time current, mu naught times into current close to the circuit, mu naught times current close to the circuit. So what is Ampere circuital law? Ampere circuital law states that the line integral of the magnetic field, around any closed circuit is equal to mu naught times the total current passing through this closed circuit, which is called Ampere circuital law. Ampere circuital, circuital law. So see, basically what happened, what do you mean by that? Suppose you have a closed loop in which, suppose this is your I1 current, this is your I2 current, this is your I3 current, this is your I4 current, this is your I5 current. So what is my total closed current in this closed surface? What is my total current? In this closed surface, what is my total current? I1 plus I2 plus I3 minus I4 minus I5. That is my closed current or total current. Is it clear? Now, the proof of this Ampere circuital law. Now, the proof of this Ampere circuital law. Proof. So, suppose this is your infinitely long current carrying conducting wire, and P is a point which is at a distance R from this infinitely current carrying conducting wire. We know if this is my current, so magnetic field is into the page cross. So, and here it is out of the page. So this is inside and it's moving like this outside. So it make a circular turn, So we have to prove this one, Ampere circuital law. So we can say left hand side integration of B dot DLC. Here the magnetic field and length vector, देखो ऐसे क्या करके, अगर ये मेरा करंट कैरिंग कंडक्टिंग वायर है, मैग्नेटिक फील्ड भी ऐसे घूम रहा है और सर्कुलर लूप भी ऐसा है. So magnetic field and length vector, they always makes an angle 0 degree. So this B dot dl is equals to integration of B dl cos 0 degree, that is B into dl, B into, what is the circumference of the circle? 2 pi r. So my B dot dl is B into 2 pi r. We know for infinitely long wire, magnetic field is mu naught I by 2 pi r. If we put this value in equation 1, so that is mu naught I by 2 pi r into 2 pi r, this 2 pi r cancel. So mu naught I. So my left hand is equals to right hand side. ठीक है ना, left hand right hand मिल गया, मतलब left hand right hand नहीं, sorry, left hand right hand बोलना गलत होगा. B dot dl is mu naught I. Clear everyone?
Yes, sir.
This derivation is very important. By using this Ampere circuital law, we can find out the magnetic field at any point. So next, very important derivation. By using Ampere circuital law, find out magnetic field due to an infinitely long hollow cylinder. So suppose You have a infinitely long hollow cylinder. You have an infinitely long hollow cylinder. Radius of the cylinder is R. Radius of the cylinder is I. R. I is the current. Suppose P is a point which is at a distance R from the infinitely long wire. So if we use this one as a current carrying loop, so the question is that due to infinitely long current carrying hollow cylinder whose radius is R, find the magnetic field at point P, which is at a distance number 1 smaller greater than capital R, number 2 smaller equals to capital R, number 3 smaller less than capital R. I think you remember same type of thing in Gauss's theorem also, outside the surface, on the surface, inside the surface. Here also outside the surface, on the surface, inside the surface. Only difference is that in Gauss's theorem you use a surface, means the aerial integration, and here the integration is a line integration. Matlab it just loop, it just complete the loop, it just enclose, not it just close, not enclose. Okay. So from Ampere circuital law, case one, smaller greater than capital R outside. See, smaller is greater than capital R. So we can say from Ampere circuital law, we can say B dot dl equals to mu naught I close. How much current flows by this loop? I amount of current. And what is the angle between magnetic field and length vector? 0 degree. So we can say B dl cos 0 degree mu naught I integration of B dl mu naught I B integration dl mu naught I B into 2 pi r mu naught I B equals to mu naught I by 2 pi r, means B is inversely proportional to R. Clear, everyone? Everyone, is it okay?
Yes, sir.
Everyone, is it okay?
Yes, sir.
Now the case 2. Now the second case. Case 2. So for the second case, small r is equals to capital R. Second case, small r is equals to capital R. Small r is equals to capital R. So this point is not outside. This point is not outside. Same like Gauss's theorem. This point is not outside. Now P is the point on the surface. P is the point on the surface. So how you find out? Everything is same, only smaller become capital R. The smaller become capital R. That is equals to constant. Everyone okay? Case 2. So if you want, you can note down. Or you can take a screenshot. Everyone done? আমি যাদেরকে এটা notes পাঠিয়ে দেব. Now case 3. So in case 3, small r is less than capital R. Case 3, smaller less than capital R. So now this point is inside. Now this point is inside. Now this point is inside. Suppose P is the point which is at a distance smaller. We know outside hollow, inside as it is a hollow. So how much is the current? I close. I close is 0. Yes or no?
Yes, sir.
As it is a hollow cylinder, the current inside the cylinder is 0. So what we can write? We can write B dl cos 0 degree mu naught into 0. So B in integration of dl equals to 0 equals to 0. So if you want to draw graph, small r is equals to capital R, then it's inversely proportional. B is inversely proportional to R. B is equals to mu naught I by 2 pi R less than, greater than. So yeah, everyone.
Yes, sir.
Okay. So this is the third case for infinitely long hollow cylinder. Now one more which is very, very important. The everything is same, just only inside the instead of hollow cylinder, if it is a solid cylinder. So my next question is find the magnetic field at point P, which is at a distance r, small r, for an infinitely long solid cylinder of radius capital R. So first and second case same like Gauss's theorem, they are same. Okay. First and second case same like Gauss's theorem, they are same. So, but the only difference is now it's a solid. So P is the point outside the cylinder. Let R is the distance. Let R is the distance. So I can imagine a solid cylinder like this. So same current flow, case one. So my this part is changed. Now my this part is same like the previous one. B dot D dl cos 0 degree magnetic field and length vector are in the same direction. That is mu naught I. The total current flows by this solid cylinder is I, which is B dl mu naught I B into 2 pi r mu naught I. B is mu naught I by 2 pi r, which means B is directly inversely proportional to R. Clear, everyone? Case one exactly same. Everyone, is it okay?
Yes, sir.
Now, case two and case one are exactly same. Case one and case two are exactly same. The only difference is in case two, instead of smaller, it's a capital R, means on the surface. And in the figure, it's not on the, it is not outside, it is on the surface. So my P point is on the surface. It is on the surface. Small r is equals to capital R. So everything is same. Here it is capital R, here it is capital R, and that is equals to constant. So if you see case one and case two, solid cylinder and hollow cylinder, they are exactly same. Solid cylinder and hollow cylinder, they are exactly same. Yes or no?
Yes, sir.
Only the difference is in the case three. In case of hollow cylinder, no current inside the hollow cylinder, but in case of solid cylinder, you have a current inside the solid cylinder. So only the change is in case 3. Here you can write P for the case 2. Now in case 3, only the change is in the solid cylinder. So in case of a solid cylinder, let the point is P, which is at a distance R. So we can say this is my solid cylinder, from where we have to calculate the I close. I close. Let the radius of the cylinder is given small r. Okay. So see, first part is same case 3. Case 3, smaller inside the cylinder. Up to this is same. Now, first of all, I close. How you calculate the I close? How much is the current through this cylinder, through this enclosed surface? Total current I, total area pi r square into area of that part pi r square. Last time, if you see, when we distributed charge, that means Gauss's theorem, we use total charge by total volume into per unit volume of the Gaussian surface. Here, not the volume. Here we use the area. So total area per unit, this one. So overall, what happened? This pi cancel. So we have I smaller square by capital R square. So if we put this value, so what happened? Ki B dl cos 0 mu naught I r square by r square. So B dl mu naught I r square by capital R square. B dl mu naught I r square by capital R square. So B into 2 pi r, that is mu naught I r square by capital R square. If we write this magnetic field, that is mu naught I r square, 2 pi r को नीचे ले आएगा, 2 pi r into r square. So this r cancel. We have mu naught I 2 pi r square into r. So magnetic field is directly proportional to r. Is it clear, everyone?
Yes, sir.
Magnetic field is directly proportional to r. So in the figure, see, second part and third part is as it is, but the first part, it is not 0. It is directly proportional to r in case of solid cylinder. So that is the only difference. In case of inside, mu naught I r 2 pi r square into r, where capital R is the radius of the cylinder and smaller is the position. Otherwise, it is mu naught I by 2 pi smaller. Clear, everyone?
Yes, sir.
So if it is okay, so then let's try a numerical. If you want to take a screenshot, you can take. मैं कल तक तुम लोगों को इसका पूरा डिटेल भेज देगा. सिर्फ थोड़ा पार्ट मेरा बाकी है, ऑलमोस्ट हो गया है, सॉलिनॉइड पार्ट बाकी है, मैं आज कंप्लीट कर लूंगा. And tomorrow I'll send you. So Sijal, Okay, अब देखो, next question is a wire of radius 0.5 centimeter. Question, very important question, very important. A wire of radius 0.5 centimeter. A wire of radius 0.5 centimeter carries a current 100 ampere. Carries a current of 100 ampere. A wire of radius 0.5 centimeter carries a current of 100 ampere, which is uniformly distributed, over its cross section. This current is uniformly distributed over its cross section. Find the magnetic field. What we have to find out? We have to find out magnetic field. Number one, at 0.1 centimeter from the axis of the wire. From the axis of the wire. Number two, at the surface. Radius is 0.5 centimeter. At the surface. Number three, at a point outside the wire. At a point outside the wire. 0.2 centimeter, 0.2 centimeter from the surface. From the surface. So try this question. Okay, I'll give you 2-3 minutes for that question. I'm stopping. So for the first one, distance is 0.1 centimeter. So if we suppose a solid cylinder of radius r, the point P is inside the cylinder because the radius of the cylinder is 0.5 centimeter and the point is 0.1 centimeter inside the cylinder. So my formula, case 3, mu naught I by 2 pi r square into smaller. Now the value 4 pi 10 to the power minus 7, current is 100, 2 pi 0.5 centimeter, I can make it 5 centimeter, converted into meter, 10 to the power minus 3 square, and 0.1 centimeter, 10 to the power minus 3. So this 2 cancel, 2 into 10 to the power minus 7, 10 to the power minus 2, 10 to the power minus 3 by 25, 10 to the power minus 6. So 2 into this 200 by 25 into 10 to the power minus 3 plus 6. So minus 7 plus 3, that is 8 into 10 to the power minus 4 Tesla. Is it clear, everyone?
Yes, sir.
So this is the first part of the question. Now what is the second part? Second part of the question is on the surface. So on the, if you find out the inside, so on the surface is very simple, mu naught I by 2 pi r. R is 0.5 centimeter, 4 pi 10 to the power minus 7, 10 to the power 2, 2 pi 5 into 10 to the power minus 3. This is 2 by 5 into 10 to the power minus 5 plus 3. So 2 by 5 into 10 to the power minus 2, 0.4 into 10 to the power 2, 4 into 10 to the power minus 3 Tesla. This is the second part. And the third part, outside 0.2 centimeter. So that is overall 5.5 plus 0.2, that is 0.7 centimeter. So mu naught I by 2 pi r, 4 pi 10 to the power minus 7, 10 to the power 2, 2 pi 7 into 10 to the power minus 3, 3 centimeter. So what you have, this guy 2 by 7 into 10 to the power minus 4 Tesla. Clear?
Yes, sir.
So after that, After that, next is solenoid. After that, next is solenoid. So what is solenoid? What is solenoid? Suppose this is my cylindrical form where I wrap a winding wire like this. So my current, this is incoming current, this is outgoing current, and the current is moving like this. So this is the length of the solenoid. So we can say one thing for the solenoid. If this is my direction of current, my thumb represents the direction of magnetic field. So my magnetic field inside the solenoid is look like this. You know this from class 10 also. And inside the magnetic field, we have to prove the solenoid ka magnetic field is N mu naught I, and outside the solenoid, magnetic field is 0. Outside the solenoid, magnetic field is 0. So for that, outside the solenoid, magnetic field is 0. Ab dekho, if we increase the length, the inside these are more stator, और ये inside में जितना stator होगा, outside में they meet in a very large distance. As they meet in a very large distance, so basically outside the solenoid, the concentration of magnetic field lines is very less. The concentration of magnetic field lines is very less. ये इतना less हो जाता है कि we can suppose it 0. And now to this, if we suppose this is a solenoid and we have to prove that the magnetic field inside the solenoid is N mu naught I, where N is the number of turn per unit length. Number of turn per unit length. So I have to show it how you prove that. For that, it is better you can draw a structure like this. This is also a representation of a solenoid. Now see, here the magnetic field are into the page. As the magnetic field are into the page, so we can write it cross. We can write it cross. And here the magnetic field is out of the page. So we can write here dot. So here the magnetic field is into the page cross. Here the magnetic field is out of the page cross. So if these are the same figure, it will show you in a better way. You can visualize it much better way. And inside this, the magnetic field is straight line, and outside this is magnetic field is 0. So to show you the calculation, I'm removing that solenoid. Now see here in this one, let we suppose a rectangular loop. Let we suppose a rectangular loop P, Q, R, S. If we suppose a rectangular loop P, Q, R, S, let L is the length of this imaginary rectangular loop. So we know B dot dl, that is integration of, this is the magnetic field. We move from P to Q, move from P to Q, B dot dl, we move from Q to R, B dot dl, we move from R to S, B dot dl, we move from S to P, S to P, B dot dl. Now see, when we are moving P to Q, magnetic field and this length vector, they are 90 degree to each other. So we can write P to Q, B dl cos 90 degree. Isn't it? Everyone satisfied? Magnetic field and length vector.
Yes, sir.
When we move from Q to R, see, this Q to R point is outside the solenoid. So my outside the solenoid magnetic field is 0. As my magnetic field is 0, I can write it 0 because my magnetic field is 0. Now when we move from R to S, again my magnetic field and length vector, makes an angle 90 degree. RS B dl cos 90 degree. When we move from S to P, see, only this one will move like this. Only this one. See, length vector and magnetic field are on the same direction. So we can say B dl cos 0 degree only from S to P. Now, if we calculate this value 0, this value 0, this value 0, this value is B S to P dl, which is B into L. Why L? Because the length of QR or SP is L. Let it be equation number 1. Is it clear, everyone?
Yes, sir.
Now, from Ampere circuital law, we know B dot dl, that is mu naught I close. Now see, this current, each current is I entering, leaving, entering, leaving, entering, leaving, entering, leaving. So for each, the value of the current is I, and let for that portion, total number of loop is n. मतलब अगर मैं एक टर्न, दो टर्न, तीन टर्न ऐसे करके लूं, if up within that the turn is n, so current into each turn. So I can say my total current I close within that loop, that is current into total number of turns. Yes or no?
Yes, sir.
So I can write my B dot dl, that is mu naught I n. Let it be my equation number 2. And this n, that n is number of turn per unit length into length. Where n is, you can write where n is number of turn per unit length. So my B dot dl, that is, don't write this one, equation 2, mu naught I n L, equation number 2. Now from equation 1 and 2, see, that is also B dot dl, that is also B dot dl. So I can write B into L, that is mu naught I n L. I can write this, that part, that blue part. From equation 1 and 2, this is my equation number 1, this is my equation number 2. From equation 1 and equation 2, from equation 1 and 2, I can write dl, that is mu naught I n L, mu naught I n L. So I can cancel this L. So my magnetic field is n mu naught I. Proof. This proof is very, very important for solenoid. This proof is very, very important for solenoid. Clear, everyone?
Yes, sir.
Acha, with this proof, examiner can give you some time in entrance exam, not in the board exam, sometime in entrance exam. Here we suppose the length of the solenoid is very, very large, infinity. So if this is my middle point, let this angle, this is my angle. If this is infinitely long, so this angle is increasing. So general equation is n mu naught I by 2 sine, this angle is theta 1 and this angle is theta 2. So sine theta 1 plus sine theta 2. This is the general formula. And if for infinitely long wire, theta 1 and theta 2 both 90 degree. So B is n mu naught I by 2 sine 90 plus sine 90, that is n mu naught I by 2, 1 plus 1 is n mu naught I. So this is for my infinitely long wire. Okay.
Yes, sir.
Okay. If it is okay, next is toroid. So what is toroid? So if we use a solenoid and make it a circular, that means if we use a solenoid, and make it circular like this one, then this is called toroid. So if we make it circular, then this is called toroid. So I'm trying to make it in a very थोड़ा zoom करते हैं, इसको बड़ा करके दिखाते हैं कि how I do it. So toroid is a circular solenoid, you can say. Toroid is a circular solenoid. Toroid is a circular solenoid. The wire is winding like this. तुम लोग अगर कैप्टन अमेरिका आयरन मैन देखा होगा, सो आयरन मैन के पास जो आर्क रिएक्टर दिखाता है, बेसिकली वो आर्क रिएक्टर नहीं है, वो एक टोरॉइड है, ठीक है। उसमें थोड़ा ब्लू कलर का लाइट दे दिया है और उसको आर्क रिएक्टर बना दिया है, ठीक है। तो बेसिकली वो एक टोरॉइड है। और तुम लोग अगर देखोगे कैप्टन अमेरिका का आयरन मैन का हार्ट में जो लगाया हुआ था आर्क रिएक्टर, दैट इज आल्सो अ टोरॉइड, ठीक है। ऐसा ही देखना इसका शेप था और इसमें कुछ वायर वाइंडिंग किया हुआ था, ठीक है। सो लेट दिस इज द सेंटर, दिस इज द इनर वायर। दिया नहीं। So A is the inner radius, B is the outer radius. So we can take a average radius, this one. Let R is the average radius. How you get this average radius? Very simple. Inner radius plus outer radius by 2. Let I is the current and let magnetic field and length vector are in the same direction. So we can say from Ampere circuit law, law B dot dl mu naught I close. So B dl cos 0 degree mu naught I. I is my current and let N is the total number of turn. N क्या है? Total number of turn. So B dl, that is mu naught In, B into dl, that is mu naught In, B into circumference of the circle 2 pi r, that is mu In. So magnetic field is mu In by 2 pi r. कभी कभी इस क्वेश्चन में कहता है कि prove that magnetic field inside the toroid is n mu naught I. So how you prove that? It's very simple. Total number of turn, we can suppose number of turn per unit length into length. और ये जो मेरा length है ये क्या है? Circumference. So we can write 2 pi r. If we put it here, so mu naught I n into 2 pi r by 2 pi r, 2 pi r, 2 pi r cancel, n mu naught I. Got it? So if they ask you to prove that magnetic field inside the toroid also n mu naught I, from here you can put this and then you write total number of turn per unit length into length. L is the circumference. So 2 pi r, this 2 pi r cancel, n mu naught L. Clear everyone? Is it okay?
Yes.
So इसके बाद इसके ऊपर toroid and solenoid I want to show you two numerical at least. Okay, and then we can say this chapter is done. So from the next class we start a new chapter, that is electromagnetic induction. और अगर तुम लोग बोलोगे मैं इस चैप्टर के ऊपर कुछ एक्स्ट्रा और न्यूमेरिकल आई कैन ट्राई. ओके, प्रीवियस ईयर्स कुछ क्वेश्चन कर सकते हैं and then we start the new chapter. So let's try to numerical from this topic, solenoid and toroid. Questions are very simple. देखो ये सब का प्लस पॉइंट क्या है, ये सबसे क्वेश्चन जो है बहुत ही प्रेडिक्टेड क्वेश्चंस आता है, मैकेनिक जैसा उतना कॉम्प्लिकेटेड क्वेश्चंस नहीं आता है. फर्स्ट क्वेश्चन इज अ सोलिनॉइड ऑफ 300 number of turns per meter. So number of turns 300 per meter. Okay, is carrying a current of 5 ampere. Is carrying a current of 5 ampere. The length of the solenoid is 0.5. The length of the solenoid is 0.5 meter, and has a radii of 1 centimeter, and a radii of 1 centimeter. Find the magnitude of the magnetic field inside the solenoid. So देखो, we know magnetic field inside the solenoid is n mu naught I. तो पहला बात है ये दिया है बकवास, क्योंकि मुझे नंबर ऑफ टर्न जब दे ही दिया है पर यूनिट लेंथ, तो मुझे वो सब कुछ भी नहीं चाहिए. I simply write 300 4 pi 10 to the power minus 7 into 5. There is 5 10 15 20 60 into 10 60 pi, 60 pi into 10 to the power minus 5. That is 6 pi into 10 to the power minus 4. Is yes or no?
Yes, sir.
So this is my first question. Now the second question. Second question to or easy है. A toroid of total number of turn. A toroid of total number of turn. इस बार दिया है total number of turn कितना है 1000. A toroid of total number of turn 1000. Inner radii 8 centimeter. Outer radii 12 centimeter. Outer radii 12 centimeter. Carrying a current 5 ampere. find the magnetic field inside the toroid. Find the magnetic field inside the toroid. So we all know R, how we find out A plus B by 2. So 8 plus 12 by 2, that is 10 centimeter. Magnetic formula is mu naught I, total number of turn by 2 pi R. So see, everything is given 4 pi 10 to the power minus 7. Current is given 5 ampere. Total number of turn is given 1000. 2 pi 10 centimeter 10 to the power minus 1. So 2 pi gaya. 5 5 10 minus 4 plus 1. So 10 into 10 to the power minus 3. 10 to the power minus 2 Tesla. Clear, everyone?
Yes, sir.
So that's it for today. Okay, that's it for today. हम लोग नेक्स्ट क्लास में या तो कुछ न्यूमेरिकल नया करेंगे या न्यू चैप्टर स्टार्ट करेंगे, ठीक है?
Okay, sir.